In the lab, but yeah, I'm sorry, in the lab, this course. Yeah, a balloon and a straw, okay? These are obviously things in their own right. There's nothing wrong with having a discussion about a balloon and a discussion about a straw. However, the majority of the systems that we're going to design and build this semester will not be primarily made out of balloons and straws. It's possible that we could have a balloon and straw making competition. That's not a problem. We have lots of systems that are based on high pressure air and pipes that run the air through those things. Most notably, we're dropping some vocabulary words. They're called pneumatics. That's that high pressure air or that high pressure gas. If we change air to the word gas, you could talk about high pressure water vapor, which is a gas, and then the English word for that is steam. And you start talking about steam powered technology. Industrial revolution wise, that was the way to roll. Almost all factories were based on steam power. We had steam locomotives. We even had steam cars. Today, in 2016, I think it was 2016, we actually heat this building with steam. So we still use steam. Steam is not antiquated. But, gosh, riverboats were steam powered. Again, trains, locomotives were steam powered. Our international unit for power, called the Watt, was named after James Watt, who's no longer with us, but he was a Scottish engineer who did a whole bunch of stuff using steam engines. He's a very, very famous steam engine engineer, so we actually have immortalized his name because of his work with steam. We looked at these components as systems on Monday, and this is something that we're going to be doing all semester. It's something that we're going to be doing as systems thinkers all your career. Sometimes it is easier to use a stand-in item that has most of the qualities that you want, and then you can talk about that stand-in item because what you really want to talk about either A, doesn't exist yet, or is too dangerous to work with. So say we were talking with high pressure, high temperature steam, that's kind of dangerous as a human to say, hey, let me go fire up a coal-fired engine, let me go ahead and get a lot of steam, and now I'm going to hold the steam in my hand, not a big thing. But I can fill the balloon with breath, and as a stand-in, we could say that's where the steam is, or that's where the steam goes, okay? So our text and our author calls this working with systems or designing systems by analogy. So we all know what an analogy is. Sometimes analogies or analogs are very, very close. They're almost exactly the same thing, where you could say, well, for the purpose of sweetening your drink, you could use sugar, or you could use the pink stuff, or you could use the yellow stuff, or you could use, what color is stevia? I don't even know. All these different sweeteners, okay, they're all sweeteners, but you don't necessarily have to talk about the exact product. You can talk about a stand-in, a substitute. That's almost a perfect analogy when talking about sweetness. In this case, how this balloon behaves and how a steam engine behaves, they're close analogies. The closer the analogy, the better. The problem is, the thing where you get in trouble as a systems thinker is that you think about building something new and it's completely based on the analogy, and then you forget that what you're really working on has some differences. We have to be aware of where the differences show up. But we definitely know that we looked at system-wise, we looked at this balloon as a system. We said it has inputs and it has outputs, and oh, by the way, it has gas or air as inputs and outputs. Just to get goofy, we said it was material both ways. And the process inside, what it does for it, we said primarily, even though it picture-wise, the balloon has air coming in from the left and air leaving from the right, we know, because we can play with an exact balloon, we know that the in and the out is the same item. Okay? So I'm using my lungs, which quite honestly can be an analogy for a balloon. That's what my lungs are. I have the same place for air to go in and go out. When my diaphragm opens up the balloon, it pulls air in and then squeezes the air back out. So we could be talking about lung function, the system of respiratory system, using balloons. But what it does in reality, system-wise, does not necessarily have to be an exact copy up on the board. But we said the balloon, what it does, or what its process is, we said it's probably good for holding air. That's what a balloon does. We fill it up, we hold on to it. The concept is we then take that air, all the air that we need, and we take it to some place where we need it somewhere else. We can store it, okay? Pop quiz. A situation where you might need to fill something here and then use the air somewhere else.
Scuba diving.
An oxygen tank.
So many thousands of things. Yes, sir?
Scuba diving.
Scuba. Everybody knows what scuba stands for?
Should know.
It's an acronym. Self-contained underwater breathing apparatus. That's what scuba is. So it was a system. They developed this system, and what's the? I'll pick on you because you. What's the primary component of a scuba system? I guess I'm going to say maybe the tank. Maybe the regulator is the most important, so your lungs don't explode because of the high pressure air. But the idea is you fill this tank, which is for all intents and purposes a balloon. You fill it with a heck of a lot of pressure. It goes through the regulator, again, doesn't let all the air pop out, and then you breathe from it. Okay, so a scuba tank is a fantastic. You had another example.
An oxygen tank? Like
An oxygen tank, somebody who needs oxygen. Yeah, so we have all these derivations of scuba divers. We have astronauts that need air. We have firemen that need air. They wear tanks on their back just like the scuba divers do. So this idea of holding air may be important because we need the air itself, but another way to view the system is that we can look at what the air does. So high pressure air can make things happen. One of those things that might happen is we can take maybe a little fan or a pinwheel. Okay. Anybody ever played with a pinwheel thing where it's on the end of a straw, you blow on it and it spins? So you're using the air in your lungs to do that. You can sort of imagine that you could fill up a high pressure balloon and then take the balloon over here and have it let the air out again and move the pinwheel. If we do that, if we literally take this high pressure air and then turn on the pinwheel and have this spin, whenever we have something spin, then we can generate energy. We can use it as an energy source or an energy device. Okay. So of course I brought along my air hogs. I think I used my air hogs last year, did I? Yeah. So if you haven't seen this before, Air Hogs is a company. It's been around for a while. My son is a sophomore in college right now, but I'm sure we bought this when he was 2 or 3. It used to be. It's not remote control. It used to have a nice wingspan of styrofoam wings. We've flown it so much that the wings disintegrated. They all broke, and we had so much tape. We had more duct tape on it than wings. But at its core, the Air Hogs is a balloon, and the balloon is actually made out of the same polyethylene terephthalate, the same material that soda bottles are made out of and water bottles are made out of. And what you do is you fill this with very, very high pressure air, and then the very, very high pressure air goes through tubes and goes through special tubes that are designed as a piston engine, a pneumatic system. The same engine, the same type of pneumatics as a locomotive, and of course that spins the propeller. Okay, so without further intrigue, the system. I think Air Hogs as a company is still around. I think Air Hogs now sells drones. I think they actually sell remote control drones, which is kind of cool. I don't know that they're all air powered. That was the deal. You wouldn't have to buy a gasoline engine or anything like that. You could just literally pump this up, makes it safe for kids, of course, without sticking their fingers or toes into the spinning prop. But what you do is you fill this up. I think I kept this filled up. It could be that I hadn't done anything because this wasn't attached. All this does is this fills up this bottle. This balloon does not expand very much because it's a pretty strong balloon, just like a water bottle. A soda bottle has under a lot of pressure when you go ahead and crack it. But I can tell right now it's kind of rigid. And the idea is if I spin this, the air will flow through here, go through this little spring and piston. It's not very high. And then it'll fly through the air. Of course, I put the wings on it. That's the power. I didn't pump it up that high. If I made sure sort of just going back and forth right now. If I made sure this connection was a little bit better, you would get about 30 or 40 seconds out of the It's pretty cool. You just give it a shot and off it would go. So this job is we're using the energy that we stored inside this tube to now use the energy somewhere else. And that of course, is technology. It's a tool, and it's also sort of what engineers do when they build things. We had this conversation last semester for those of you who were with us in the physics class. The word engineer, even though it sounds in the word English, in language English, it sounds like we're talking about an engine, like a steam engine. It's closer to the word ingenious. That's what engineers are. They're ingenious designers. They invent stuff. Scientists typically discover new things. They find out how things work. And then it could be the same person. A scientist could be an engineer and a scientist. But typically, after the scientists discover how these chemicals react or how strong this material is, they hand it over to the engineers, and then they build cool things about it. They design new things. So this idea of let's pump this up, and then let's use it through this special system, which happens to be a piston system, later on, then we can move the energy from, don't bother me, I'm filling this thing up, I have a certain amount of time, and then we can decide on how much energy we need later on. The reason why I bring this along, and of course this is air systems or pneumatics, is, we mentioned this in lab on Monday, we're not going to be using air systems, we're going to be using high pressure electrons as opposed to high pressure air. There's absolutely nothing wrong with high pressure air. It's a fantastic system. We have lots of things that run on high pressure air. However, we also have lots of things that run on high pressure electrons. So rather than talking about a balloon, we're going to talk about a battery. Okay. Input, output, and primarily the reason or the process for a battery is also like balloons for holding stuff. Okay. And what does it hold? Well, again, I mentioned that it's not going to hold air, it's going to hold electrons. And if you remember your high school chemistry, we have these little atoms, and there's a proton inside, there's an electron out the other side, other atoms have neutrons, and most often, cartoon-wise, we can think of electrons being these little tiny marbles. And these little tiny marbles, they're tiny marbles, that's one model to use. They're negatively charged, and if we put enough of these negatively charged electrons inside the battery, then it will pump up, just like the balloon does. And then when we stop pumping it up and we let it back out, the electrons will flow back out. Okay? So while the balloon is full, we have high pressure air, and while the battery is full, we have high pressure electrons. Okay? So the analogy is very, very close. As far as its process, it's extremely close. Unlike the balloon, which only has, well, this, you can conceivably design a balloon with two ends, and one in, one out. This balloon has a single opening, and it does double duty. Okay, you use this side to put it in, and this side where it comes out. That's a little bit different with the battery. The battery literally has one side in and one side out for the electrons. Okay, so if I put these guys up here like this, in fact, let me go ahead and draw it properly. Here's our battery. The wording's upside down. If I draw this exactly like I'm holding it here, there's the little dimple on the other side. Here's ever ready on this side. And this guy happens to be the positive side, and this guy is the negative side. And again, it's difficult to say where the input and where the output is. It's almost like a balloon. What happens is inside here, the way this is an analogy, it's not exactly, but chemically, this is a chemical battery. Inside this chemical battery, chemically, we take the electrons that are normally all over the place, because these things are neutral atoms, and we move them from the positive side to the negative side. And when you remove electrons from a neutral system, when you take it from one side and give it to the other side, then this side is missing electrons and becomes positive, and this side has extra electrons and becomes negative. Okay, that's the analogy. And if I go ahead and look at this battery, it helps me out. It says the side with the big dimple up here, it says there's a plus symbol. That's the plus side. Okay? And and then this is the negative side over here. Okay? So if I either chemically or somehow, we don't do it chemically, anybody happens to carry this thing around called a smartphone, okay? It happens to have a battery in it as well, and at night you plug it in. What happens to the battery inside a smartphone? The electrons from one side are constantly pushed and moved to the other side until when you take it off the charger, you have a whole bunch of extra electrons on this side, and you're missing electrons on that side. Okay? If the battery short circuits or the battery explodes, what happens is whatever mechanism is keeping them separate, it collapses. And this guy immediately goes, it shorts out. So I had my goofy little fun where I took the balloon and I popped it on Monday. That's what happens to a battery if it shorts out. Does anybody know what happens to a real battery if you short it out? Just like the balloon, right? It often explodes or catches on fire. That's what's happening with the Teslas. That's what's happening with the hoverboards. Have you seen the hoverboard craze? The hoverboard craze is they're shipping these hoverboards with these... The hoverboards need a lot of energy to keep some heavy 50-year-old guy like me vertical and not fall over. That takes a lot of energy. So they put a lot of energy in those batteries. And the batteries are just straining like hell to have the high-pressure electrons go back. And this barrier that they're using or they've engineered, it's breaking down. And when it does, the batteries explode and they catch on fire. I hate to say that so nonchalantly, but hope no one got hurt. Same thing with the electric cars. Not all of them, but Tesla very famously had an electric car or two catch on fire and burn down because their system collapsed. These guys have been around for a while, okay? And what we do is we typically, this guy's charged up. I'm using him, again, nonchalantly. There's a lot of energy inside here, just like playing with a balloon that's popped up. What I can do is to allow the electrons to go back the way where they used to be. I can destroy this. It's not a physical connection. It's a chemical barrier, but there's a barrier between the positive and the negative. What I can do is I can allow the electrons to flow out of this side, the output, and then come back around to the input. Okay? So instead of just having the wall collapse and the electrons go back where they belong, I can force them to take a long trip around. So just like our straw with our balloon, we can use a straw to sort of direct where the air goes. We can direct where the electrons go. And it turns out, you guys already know, we're not learning anything new here, we're just sort of agreeing. The straw inside electronics is a conductive wire, a wire that conducts electricity. To our eyes, and honestly to our fingers, this is not hollow. This is hollow, because we know gases to flow through a hollow space. This is not hollow, but it is hollow, pardon the analogy, it is hollow to electrons. Electrons flow through this. This is, the analogy that we use for wires is very similar to a garden hose that's hooked up to the spout over here. Let me draw a really crappy spout with a turn valve up here. You take your hose, here's this long garden hose, okay? Inside it, it has these molecules of H2O the whole way through. So we would say that a garden hose that's filled with water is not hollow, because it has water in the middle of it. But if I turn on the garden hose, and I'm able to squeeze in one more molecule of H2O, what happens to all the molecules that are already inside the hose? They get bumped or moved over or displaced. So that goes there, and this goes here, and this goes here, and that goes there. What happens when we're done? One molecule of water spots on the other side. So we continuously do this. So even though the hose is not hollow when it's filled with water, and we use it for water, if we push water in one side, water instantly, instant's a very dark word, starts coming out the other side as long as the hose is full. It's the same thing with these wires. These wires are filled with electrons, but they don't have extra electrons and they're not missing electrons. It's just enough electrons to fill it. But as soon as we push an extra electron this side, they all bump over and one electron spits out the other side. That's sort of how this works. It's not hollow, but it's filled with electrons because the conductive metal inside this wire allows those electrons to jump from one to the other. So we're able to use this wire to connect the negative terminal to the positive terminal of the battery, and then what happens is the electrons can flow. We typically, again, this is all a review, I'm not teaching you anything. Geometric shape that we've drawn here. It's not a triangle, it's a circle, it's an oval. Sort of we were talking about Pneumatics, the circle of life. Okay, it's a circle of electronics. This idea of the electrons going from an area of very high pressure electrons around the other side back over to where we're missing electrons, which means it's positive. That's a circle, and of course we call the entire thing a circuit. So if not electronics circuit, is anybody, is Zumba circuit training? I'm not really sure. Anybody circuit train exercise-wise? You go around the circuit, go around the gym. You do this for a while, then you do this for a while, then you do that for a while. It's a circuit. You go through a cycle. Maybe you do 3 of those cycles. So all of those words, circle, cycle, circuit, they're all analogous. We're going to be talking about electrons running around this circuit. If this circuit is broken, and there's no way for the electrons to make it back to where they'd like to be, then we call that an open circuit. It's open. As long as the circle is not broken, we call it a closed circuit. Okay. If for some reason the battery is damaged and the electrons take a shortcut and then it causes it to explode, we call it a short circuit. Okay? So there's the open circuit, there's a closed circuit or a full circuit, and a short circuit. We want to avoid the short circuits because typically things go badly when that happens. Just like we can take the high pressure air and then return the high pressure air to the atmosphere, just like we took high pressure air from the balloon and returned it to the atmosphere, we can run that high pressure air through a specially designed circuit, through a specially designed machine, through a specially designed engineered path. This path, and we can see it from there, has a little piston inside of there, turning on a spring, and every time it runs past this piston, it's like somebody has pedaled on a bike. So every time the pedal goes down, it's like someone has taken their foot and pedaled down this bike. That's what spins this. Okay? So what we can do is, scientists and engineers have discovered, we can run this wire through a very complex machine, and we typically call this a motor or an engine, however you want to call it. It's another system that happens to be a fast pedaling device. Okay? So of course I brought this guy along. For those of you who were with us last semester, we used this guy as a fan. It also looks like the air hogs. It has the propeller out front. This also has a place to store high pressure stuff. This guy happens to store high pressure electrons in the form of batteries. I happen to have 4 batteries in this circuit, all connected together. And right now, this circuit is open. There is another system over here, another component. It's called a switch. And right now, it is open. It's like a drawbridge or a door. It is not allowing the high pressure electrons on the negative side of the battery to go through the motor, which is inside this plastic, spin this guy, and then go back to the other side of the battery because this switch is open. The way I close it is I turn the switch. This is made out of wood. It won't hurt me, but it does sting like a son of a gun, so I'm going to make sure I'm out of the way. I'm going to allow the electrons to leave the negative side of the battery, run through wires inside this device, go through this motor system, which spins this as it goes through, it causes it to pedal, and then it goes to the other, rather than spilling back onto the floor, it goes the other side. So that's a lot of power. Okay? Now we can use our ears to find out if it's slowing down, because we know that sound will come down in tone. sort of being pretty constant. You can feel the air. I don't want to hurt Lewis, but don't put your finger in it. You can feel the air coming. Okay? So what we can, and I open the circuit again. Okay? So we can use this as a machine. When we did this last semester, we mounted this to a little car and it moved one direction like a little sled. We have airboats. And if you have a giant airplane and you have enough batteries, you can turn it on and say, we're going to go ahead and fly across the United States. And off you go. And keeps on going. So we can turn this into a machine. Okay? The actual details of what goes on, obviously there's lots of details to make this work. However, systems-wise, it's pretty simple. We have a battery. In this case, we have 4 of them providing lots and lots of flow of these electrons. Runs through wires inside here, runs through a special system called a motor, which actually creates a pedaling motion. The pedal moves the propeller. It goes through this switch. We either open the switch or close the switch, and it goes back to the battery. Because you guys are familiar with balloons, and because you're familiar with cell phones, what happens when all of the high-pressure electrons eventually make it back to where they belong on the other side of the battery? What happens to the system when the batteries
Becomes dynamic. You have electricity.
We do, but what happens after I let this run? I just put it here and I'll let it run for an hour and then come back. It runs out eventually, right? Because just like I can only ever fill this balloon with its maximum amount of air, I can only ever fill these batteries with the maximum amount of electrons. If I try to overfill the balloon, it explodes. If I try to overfill the batteries, they explode.
No, you don't.
They do.
No, you don't.
No, they really do.
No, they don't. I overcharge my phone every day.
No. Okay, so what you're telling me is the company that makes your phone
Right.
sold you this battery
Right.
and then put it onto the charger,
That's
right? And you can let it charge for weeks at a time.
I don't let it charge for weeks.
Okay,
But based on what I have done, I let it charge for like 2 days or one.
Fabulous. Okay. What happens to your phone when it says 100% charged? What happens to the charging system?
No, okay, it can break eventually, but it hasn't broken.
No, I'm not trying to disagree with you. I think we're saying the exact same thing. The charging system knows when to stop pumping it.
Oh.
Yeah. Otherwise, if I sold you this phone
Uh-huh.
and I gave you a charger and I said, after 3 minutes, you better unplug it or it's going to be bad. It's going to burn down your house and maybe you and your kids will die. But give me $1 and I'll sell it to you. Okay? That happens once or twice, God forbid. And all of a sudden they fix it. So yeah, when you charge your phone, it has a circuit inside there. It's already been designed that it can't overcharge the battery.
Okay, so I can just
leave it
for a whole week and it's gonna be
It's
fine.
good,
It's not-
yeah. It'll
on fire.
Unless it's broken. Because there's millions of people using batteries and millions of people using battery chargers, and sometimes, just like when you step on a skateboard, it's not working. If the charger is malfunctioning, it's possible that it will overcharge the battery and your cell phone will catch on fire. It happens. It just happens.
Just by app.
But it's just by accident, unfortunately, but not by design. But there's a lot of safety engineers that go into designing this system that when they recharge it, that you can't overcharge it because you as the user did something wrong. They try to put it into the system. So we're saying the same thing. Yeah. Fantastic. Yes, ma'am.
So you know how they say that the more you charge, let's say your phone, the faster your battery starts dying? What does that mean in terms of like system with the battery?
I like that answer. First of all, your answer was it's total bullshit. There has been studies as to whether that's true or not. This is me not knowing everything. This is me just reading the information here. So, well, first of all, it's a rechargeable battery, so it's not this chemical battery like this guy over here. But let's go ahead and have the positive and the negative again. The analogy, I'm going to use a very poor analogy. The very poor analogy is that when we charge it, we indeed move in fact, what we do is we move them this way. The charger's over here, and we actually fill this side with electrons. live inside there. This is the analogy. Whether it's true or not, this is the explanation of the people who say, they say, if I draw these little electrons as a bunch of little tiny marbles, that the marbles that are, again, this is a gross analogy, the marbles that are packed in first, they're packed very tightly and they're packed in a very tight grouping. And then we keep on filling it and filling it and filling it. The thought being, as this guy becomes higher pressure, the electrons, the analogy is, the electrons go ahead and pack closer and closer and closer and closer together. So the thought is, if you took an empty cardboard box and filled it with packing peanuts, styrofoam packing peanuts, and then you put more packing peanuts in there, and you went ahead and you just keep on pushing them down, eventually they will get really, really close and turn into almost a block of packing peanuts. And then the thought is, the argument is, as you use your phone, these electrons have to come back out. Only those electrons that are near the top or the exit of the battery are the ones that actually leave, and these guys stay behind. The analogy is, if you keep on doing that, repacking or repressurizing your box of peanuts, then that's why Fabian says it's bullshit. The old electrons that are up here that have been packed months ago, they get stuck. And when we go ahead and we let the battery turn on again, it's as if these electrons that have been packed at high pressure up here, they don't want to leave. That's the analogy. The real thought is that these are chemical batteries, they're lithium-ion batteries, and it turns out when these things have very, very strong electric fields, which is what happens when we charge this, the materials inside there actually stop becoming amorphous, which means random, and they start to align and become crystallized. And then when they become crystallized, they don't give up their electrons as fast. That's the thought. That's the analogy. So the thought is, you should use your phone from 100% to near empty, so that, again, the thought being that you'll empty out the older electrons and you'll refresh your battery. They have found enough cases for this that this analogy holds also for lead-acid batteries. Cars have lead-acid batteries. They even have a battery charger called a recycle mode, where it will literally intentionally drain your battery to zero and then repack it again. And what it does is the thought is that it removes that alignment problem. But who knows? There's a lot of marketing involved, and whenever there's marketing, there's dollars involved. And as soon as the marketers talk, we love marketers because we're ISBT. So the B says we're marketers too. The marketers go talk to the scientists, and they say, "Hey, I just heard this theory. We should tell our customers they need to do this or back and forth." We're not really sure, but yeah, I've heard of different battery systems where not cycling your battery is sort of not cool, and it dies earlier. I'm not really sure. I'm probably on Fabian's team. I think it's probably bull crap, but hey, I'm willing to learn something new. Fantastic. So our goal today is to realize that we're going to be talking about batteries, and the batteries have high pressure electrons. The high pressure electrons then flow through wires, and then the wires, if we specifically configure them from simple flow-through wires to more exotic, like pedals or motors or something that's not amazingly exotic like this, then we can cause things to happen. And of course, the most modern example of things that you can do with your electrons that are pretty cool include computers and smartphones and health. That does the same thing. And these monitors, we're using electrons running through those lights up there. We can have lots and lots of cool things happen based on the flow of electrons, which is what we're going to be talking about this semester. Does that work? Is that enough for Wednesday? Are we good? What's right? I'm sorry, I'm not allowed to say work from physics. Fantastic. Thanks, guys. Wonderful. Keep on the conversation on Friday. We're going to start talking about electronic circuits and start building some cool stuff. Cool. Bye.